Happy Monday. I hope you all are surviving midterm season okay. Um, Today, we are starting in a new topic. We're going to start in on networking. And so for the first half of lecture today, what I'm going to do, this is fun. I get to teach you my best attempt to in half a lecture, how does the internet work? Okay, so this is your speed run through networking from a non-networking person if you've never taken a networking class before. If you've already taken 168, you could disappear for the next hour and a half and wouldn't miss anything. So that was a great time to take off and go chill for an hour and a half if you've already taken 168, or to fast forward through the YouTube recording. But if you haven't, then I get to teach you. This is one of the fun things about teaching this class, is I get to teach you stuff, not just security, but other things that I think everyone who graduates with a degree in CS or EECS here should know about, some basic stuff. So that's where I'm going to start. And then we're going to jump into, with that background, looking at internet security. Okay, so we were looking at web security before, and I want to tell you, basically give you a perspective on how does the internet work. What's happening when you connect to a website or send an email or use WhatsApp or whatever. Okay. What's the internet? It's like a network is a bunch of machines that can talk to each other, send data, communicate. And then the internet is like one really big network that you could view as a whole lot of networks all combined together worldwide. By the way, classic joke from computer science is, what's the definition of a distributed system? When you can't get your work done because some computer you never heard of is down. Okay, so we're going to look at how the internet works. And of course, if you are connecting using your web browser, connect to a website, all the data between your web browser and the web server is sent over the internet, the public internet. And it can be used for many different purposes. The internet consists of a bunch of network protocols. And a protocol is an agreement about how to communicate, how to interpret messages sent back and forth, a process to use. So typically it specifies the representation of data in a network packet, what data goes where, and also what actions to take, how do we organize our communication, how does that back and forth work. So an example of a protocol would be, if you wanted to ask a question in lecture, you know what to do. You raise your hand, you wait, eventually I call on you, you don't say anything until I call on you, then when I call on you, you ask your question, and the speaker pauses while you ask your question. And if you gone a while and I haven't called on you, then you figure, oh, maybe I didn't notice you, and you do some fallback. You say, hey, can I ask you a question? Okay, so it's kind of like a standard set of roles there, where it's clear what to do at each step for each of us. That's what a protocol does. It tells me what to do at each step. It tells you what to do at each step. Of course, in the network world, the protocols can be a lot more complicated. There can be a lot of more different states you can be in, and a lot more elaborate description of what data is communicated. But a protocol is just an agreement. It's an agreement to help us communicate. And to help understand how the internet works, I think a really good analogy is mail, the postal mail. So I'm going to try to talk you through a view of how you could view paper, postal snail mail working, and then how does that correspond to the internet. So the goal of the internet is to enable people to communicate, send messages from one machine to another. In other words, send data. And in the real world, a version of that is, I want to send you a message like I'm vacationing, and I want to send back a postcard to my family saying, hey, awesome, here, I'm thinking of you. The postal system is a way that you can send messages through the physical world that's been around for oh, I don't know, 200 years or something like that. How does a postal system work? Well, first of all, the first thing we need is some way to move data. This is like a computer science view of the postal system. We need some way to move messages. So that could be like a mailman who like gets in their mail truck and they have like a basket full of letters that they like deliver to each address. It could have been some person on a horse long ago. People have experimented with, I find this amusing, carrier pigeons as a way of communicating data. One way that people would use carrier pigeons was they would train them to fly from one location to another location. And then to send a message, this is old school stuff. You'd write your message on a little piece of paper. You'd like wrap that around their leg, like attach it to their leg, and then you'd send the pigeon off to fly to the other location. And then at the other location would be the recipient. They would like take the message off, read it, like write a reply, and send the pigeon back. And I find it kind of amusing that there is an entire Wikipedia article on computer networking using carrier pigeons, where they calculate what the bandwidth of the network could be if you attached a small SD card to the pigeon, and you end up with some, throughput that is like arguably higher than we can get with, any reasonable digital communication mechanism. So that's in the real world, it's like a person on a horse. But in the digital world, it's some kind of electronic technology or lights usually. So it's like voltage transmitted over a wire, or like light beam sent down a fiber optic cable, or radio waves sent through the air. And usually it's unreliable transport. Might not get through. The pigeon might get distracted by like, ooh, birdseed over there. I'm all for that, or worse. So that's the first thing we need, a way to get data, a message from point A to point B. Then what that gives us is a way to link up people. A lot of times these ways of communicating were fairly local. Like the mailman would have a route within a neighborhood and knew how to deliver letters between any two people in the neighborhood or in the town. But we often want a way to like communicate with people further away. And the same is true with the digital world, where we'll have networking technology that can connect up all the people within an apartment building or all the devices within your home using, maybe it's a Wi-Fi network, maybe it's Ethernet running through the walls, and use that to form what's called a local area network, a network that like is within this building or within this classroom, which is great if you want to communicate with someone else in the same building or in the same classroom. But if you want to communicate with someone who's not on the same local area network, then you need something else. And for that, we need the third building block, which is a way to connect these neighborhoods, connect these local area networks. Okay? So if I want to send a letter to someone the next town over, maybe my mailman only can deliver within my town, their mailman can deliver within their town. We need a way to get the letter between the two towns. And in the postal world, the solution to that is a post office. There's a post office in Berkeley. There's a post office in Oakland. In fact, multiple of them. My mailman knows how to get a letter from my home to the Berkeley post office. The post offices have a way to get letters between the post offices, and then the Oakland post office has a way to get letters from that post office to the people in that neighborhood. So I can use that to send a letter to someone in Oakland. And in the digital world, it's the same thing. We have ways to connect up these local area networks through routers, basically. And by connecting up a bunch of these local area networks, we get what's called a wide area network, basically. Much broader than just one building or one neighborhood. And in the internet, the design of the internet is basically we want to connect the whole world. So we have a whole lot of these post offices. a whole lot of these routers. Okay, so we got a whole lot of local networks, like every Wi-Fi network in every person's home is a local area network, or the Ethernet within one building here on campus is a local network. And then there are wires that like connect these local networks to routers. Like if you have DSL, you have a wire that connects your home Wi-Fi access point to the ISP's router. And these routers, these post offices are connected to each other and enables you to send a message from your home computer to any other computer anywhere in the world. Okay. So that's sort of analogous to if I wanted to send, I don't know, a Christmas card to my aunt in New York. That happens by me putting it in my mailbox. The mailman picks it up, goes to the post office in Berkeley, and then it gets routed maybe to the one in San Francisco, and then from there maybe it gets on some plane and ends up in, I don't know, Newark, and then the Newark one gets on a truck that goes to, someplace in New York, and eventually to my aunt's town. Same deal on the internet. Okay, so on the internet, we have these building blocks get called layers of abstraction, very similar to like layering in a software, where you might have a library and then an application that's built that uses that library. Same deal on the network. We have protocol that acts as like a library, and then another protocol that uses that library, uses the lower level protocol. And in fact, we have multiple of these that are using each other. For instance, there's typically these 3 layers. Layer 1 would be a way to move bits like within a local area network. That would be like Wi-Fi. Layer 1 would be like move bits over the radio waves. So that'd be like the part of Wi-Fi that says, if you want to send a 1 bit, then send this radio wave signal. If you want to send a 0 bit, send this other radio wave signal. And then there's the layer above that enables people to communicate within a local area network, provide some addressing, provide a way to describe which machine this communication is intended for. And then layer 3 is this like collection of post offices or a collection of routers that allow connecting up to local networks. And one crucial thing about how we design networks are like really complicated. So to enable us to think about these complicated things is we have each layers provide some abstraction. So layer 2 doesn't need to understand all the details about how layer 1 works. It just needs to know like what's the API, so it can like use layer 1 as a library. And there might be multiple different implementations of that library. So it's kind of like me driving a car. I don't need to know all the details of like how the V6 engine in my, Honda works. I just know to like, press the gas pedal and the brake pedal and turn the wheel. And I can get in a different car, like a Ford or something like that, and has the same interface. I can still drive it, even though maybe what's under the hood is different. Or a Tesla, which is totally different. It's some electric engine instead of a gas engine. That's all abstracted away from me. Same deal with these network protocols. You can change out one layer and the other ones don't need to like be modified. They don't need to know that the other one has changed. So this lets us like mix and match protocols. For instance, if you've got a network that's using Ethernet and you want to switch to using Wi-Fi, okay, you can typically do that without too much trouble. Okay. So the standard way of talking about this layering, there's a standard way that you'll find in every textbook, which is called the OSI model. And it's actually a lie, but it's kind of a useful lie. Like, in chemistry, they teach you this like picture of like, I don't know, atoms have these like circles with, electrons going around. And they later tell you, well, that's not really how things are, but it's kind of like useful. Same thing here. The OSI model is not really how things are, but maybe it's a useful way to conceptualize things. So in the OSI model, the design of the internet works by defining a bunch of these layers. Each layer is a protocol. And there's some like standard that specifies how each protocol works in a given layer. And each layer uses services provided by the layer below it. Like the layer below is treated like a library, and then provides services to the layer above it. Like it's a library for the layer above it. So it's like you could think of it as like some application that's calling a library, that's calling a library, that's calling a library, that's calling a library. Except in the networking world, we call that an application that's invoking a protocol, which uses a protocol, which uses a protocol. Okay. And the OSI model says the way to build networks is with 7 layers. Except that it turns out we really only use something like 5-ish of them. So you can map the way the internet works sort of loosely to some of these concepts that are in the OSI model. Ignoring layers 5 and 6 in the OSI model, which were just like a mistake and they are not actually used. So the way that I'm gonna like describe to you how the internet works is like describing how each of these layers works. But I wanna kind of just warn you in advance, it's a lot. The real history here is the US like started to develop these networks and they're like, oh, we should connect them together. How are we gonna do that? I don't know, let's figure out something kind of ad hoc. And the Europeans were like, we're gonna sit down and we're gonna very carefully come up with a design. And they wrote thousands of pages of specifications before they built anything. Incredibly complicated document. And that document became the OSI model. And then it turned out when they went to build it, it had no success whatsoever. It was way, way, way too complicated. They had all these like ideas about how things should be, and they didn't actually try them. So the OSI model was a complete failure. The US model of let's just try to connect these things together ad hoc and like figure it out as we go turned out to work. And then after the fact, we realized some of those concepts in the OSI model are actually a decent description of how things have been ended up being built in the internet. So there's sort of a mapping there. So we like today try to make it look all nice and clean by like using these concepts from the OSI model to describe how the internet works. But it's not really true. Like it's sort of an analogy, but if you look at the actual OSI model, it has all these like very specific things that are not what the internet does. So just understand that I'm like giving you a loose, treat the OSI model as like a loose way of, I don't know, some concepts there that you could steal from it. So the OSI model has these layers: physical link, the internetwork, transport, and the application layer. And I'm going to just tell you how each one works, starting with the bottom, the physical layer. So the physical layer is the closest to like actual physical phenomena, like to electrical engineering. And what the physical layer provides, like if we have a wire with a computer on one end and another computer on the other end, it describes how to use that wire to send bits. Doesn't say anything about what bits you should send, just if you have some bits to send on that wire, how do you modulate that on the wire? So like one standard might say if you have a 1-bit, put 5 volts on that wire, and if you have a 0-bit, put 0 volts on that wire. But it could also be something more complicated. It could be like if you have a 1-bit, send a signal like this, and if you have a 0-bit, send a signal like this. Some crazy pattern. And all like this kind of crazy stuff does actually happen in real life. Okay, so if it's over wire, it might be like patterns of voltages. If it's light through a fiber optic cable, then it might be like how strong the light is, and actually like the phase of the light, so other physics properties of it. If it's like Wi-Fi or any radio communication, like cell phone, then it's something about the radio waves. Like the frequencies, the intensity, the phase, all of that stuff. And then each physical layer provides a specification that everybody can use. So for instance, Wi-Fi has a specification for its physical layer, how to turn bits into a radio wave that's like transmitted by the antenna in my laptop. Ethernet has a standard that says how to turn bits into a voltage on a wire. Cell phones have a standard. Okay, so this would be like the kind of thing you would study if you were in like electrical engineering, and you would like look at the trade-off between higher bandwidth and like lower reliability. Like I could say a 1 bit is 5 volts for 1 millisecond, and then you would get to send 1,000 bits per second. Or I could say a 1 bit is 5 volts for 1 nanosecond, and then you could, get to send like billion bits per second, but it might be really easy for noise to corrupt a bunch of bits. Okay, so your mental model is, because we're in computer science, we mostly don't think about the physics. Assume someone else has solved this for us, and conceptually what the physical layer gives me is if there's 2 devices, A and B, then they're communicating, and I have some sequence of bits that I want to send, the physical layer describes how to do that. So once you have a physical layer, you can transmit any sequence of bits you want from device A to device B. Physical layer doesn't say anything about how to interpret them. Just you have some bits, up to you to figure out what they mean. So the 2 endpoints had better agree on how they're going to interpret these bits. Okay. Maybe pause here, just see how we're doing, if there's any questions so far. Okay. Physical layer sort of would be the start if you had only 2 computers in the entire world. But of course, we have more than 2 computers. Like on a network within a building, there's multiple computers attached. And so if A wants to send a message to B, like on Ethernet, there's 1 wire that multiple computers are attached to. So like any of those computers can start putting 5 volts or negative 5 volts on that wire, and all the other computers can like monitor the voltage on that wire. And so if A has a message to send to B, there has to be some way to indicate like that this is intended for B and not C and D on the same network. So what do you do if you have more than like 2 devices in the world? That's what the link layer describes. The link layer describes how to form a local area network with multiple devices on it. And the link layer allows now, rather than just a stream of bits, sending messages, sending packets. The link layer, we call them frames, but it's the same thing. So that is some data of some particular size and a way to specify which device this data is intended for. So on Ethernet, an Ethernet frame is a chunk of data. It could be up to 1,500 bytes typically, and it has some information at the start that says, identifies which computer is supposed to receive, this is like destined for, which computer is intended to receive this, and which computer sent this. Okay, so I already said this. On Ethernet, your local area network is all the computers are connected to all the other ones. And then a frame has to contain at least 3 things: the source, the machine that is sending this message, the destination, the machine that this message is intended for, and the data, whatever the collection of like bits or bytes that form the message. So you can think of this as analogous to a piece of postal mail where you have a return address, a from address on the envelope, and you have a to address, the destination address on the envelope, and then inside the envelope is the letter or whatever with the message being sent. Okay. So now, if in the simplest form of Ethernet, this is all one wire. Any computer could send by like modulating the voltage on this wire. All the computers are always listening all the time. And so if A sends an Ethernet frame with the destination marked C, all the computers are monitoring this wire. So they all see that something is being sent. And at the start of this frame, they look at the destination. B is looking at that, C is looking at that, D is looking at that. When B looks at this frame, B will see that it says destination C. And so B will say, oh, that's not from me. I'll just ignore this frame. When C looks at that, it'll discover that the destination is for it. Destination C, that's me. I should listen to this. And then D will notice it's not for D and it'll ignore it. So that's the simplest kind of local area link, like the oldest Ethernet networks. Another example is Wi-Fi, where it's a broadcast mechanism. When my computer sends a message, it sends a radio transmission. That is, anybody with a radio receiver can receive that. So all like computers and cell phones on that Wi-Fi network are listening all the time. And when they see a frame, they check what the destination is and they say, is that for me? If so, I'll pay attention. If not, I'll ignore it. So they're all shouting at the same time. It's kind of crazy to think that that actually works. Because you could totally have A and C trying to send something at the same time. They'll be like talking over each other and nobody will be able to tell what either one's saying. But somehow it works. These networks are so fast that most of the time no one's sending anything. And so it's okay. There's not too much overlap. Now, link layers or local area networks don't have to look like this. It doesn't have to be a broadcast mechanism like radio or a single wire like Ethernet. It can also be a bunch of like pairwise wires with just connecting two devices and then form a local area network out of that. And so modern Ethernet networks often are not a single wire. There are multiple pairwise connections. That gets even higher bandwidth because then you don't have to worry about multiple devices like kind of stepping on each other's toes by trying to send something at the same time. Because they're on separate wires, they're not going to interfere with each other. So now in this more modern kind of Ethernet local area network, we're trying to pretend like it's all one wire, but it's not. It's multiple of these. And so the devices have some functionality to ensure that the frame reaches the eventual destination. So in this example, if A is sending a frame to C, well, there's a wire between them, so it goes directly. But if A was sending a frame to D, we'd need some way for it to get like through B and then to D. Can anyone guess some simple ways you might structure a local area network to make it easy to figure out how to get a frame from the source to the destination if they're not connected by a wire? Like what would be some simple graph structures that would make that really easy? A DAG? Okay, do you want to say more about why a DAG would make it easy?
They could have like a cyclic graph, like that's like basically like a tree centered at the center or at your destination.
Okay, a DAG. A DAG would make sure you know which direction to send the message. Any other suggestions or possibilities? Yeah? A tree, okay. Do you want to tell me what would be good about a tree?
If the destination then wants to send a message back, the path would be.
Uh-huh. Okay. So a tree would be better. Okay. Uh-huh. tree would make it easy to find a path between 2 points. The nice thing about a tree is there's a path between any 2 points, and that path is unique. And it's the same kind of whichever direction you're going. To go from A to B or B to A, you just reverse the order. That's true. Any other possibilities? Yeah? Those are both possibilities. Another possibility? An arbitrary connected graph. One very simple example would be fully connected graph, where every device has a wire to every other device. That would be awesome for bandwidth. You'd have a really high bandwidth network, but it'd be a nightmare for the poor, I don't know, electrician who has to run those wires. What does FedEx use? Does anyone know? Yeah? A hub system. Ah, how would that relate to this?
Like have a region where like all of the nodes are connected to like one central thing.
Uh-huh.
Then you have all the central things connected to each other.
Yeah.
So everyone reports to their local hub, and the hubs are the ones that are all like fully connected.
Yeah. The hub and spoke system, where you have in each region, you have one hub. Everybody within that region is connected to the hub, and then the hubs are connected. You connect the regions by connecting up the hubs. Totally, totally. That's like the FedEx model. Guess what? That same model is used in local area networks. In fact, today, the most common way to have an Ethernet network is a very simple topology. There's one hub. Every device is connected to the hub. Just one hub. If you want to have multiple regions, that's what the internet is for. That's for connecting up the local area networks. But you have one hub or local area network. So for any two devices to communicate, if A wants to send a message to D, A sends the frame to the hub, and then the hub sends it to D. So your hub better be pretty fast, but that's doable. Okay, so there's many ways you could organize a link layer. The link layer, there needs to be some way to identify the machines, the source and the destination of this frame. And that's typically done with an address called a MAC address. I don't know why it's called that, as opposed to like, it seems like a more natural address. Natural name would be link layer address, but whatever. MAC address is the accepted term, which basically means the link layer address, the address for purposes of the link layer protocol. And that address identifies uniquely the device on the local area network that is sending this message or that this message is intended for. And in Ethernet ensures that every device on the local area network has a different address by assigning every Ethernet card or every like computer with an Ethernet port a globally unique address. That should be different. No two machines have the same Ethernet address. So they do that with a 6-byte 48-bit value, and 48 bits is more than enough. 2 to the 48 is way more than the total number of like computers with Ethernet ever made is. So every computer has its own unique Ethernet address. Doesn't technically need to be globally unique. It could just be that locally unique within the local area network, but this works. Okay, and Wi-Fi uses the same method of assigning a link layer address as Ethernet. So like your phone, when it connects to a Wi-Fi network, your phone has a 6-byte MAC address that identifies the device. Okay. So a frame on the link layer has a source. That's a 6-byte value. That's the MAC address identifying the machine that sent it. And a destination, that's another 6-byte address that identifies the device that this should be received by. And then the data. And yeah, That's the problem the link layer solves, is to identify which machine this message is destined for and get it to that machine and enable like a neighborhood, a local area to communicate with themselves. So now that's the link layer. That's the problem the link layer solves. The link layer solves local area networks. So the next thing we want to do is we want to talk to devices or people that are not on my local network. And that's what the internet or the internetwork layer solves. It provides a way to send messages to any device in existence, not just my local network. So the network layer or the internetwork layer connects up local area networks. And what it provides is a way to send a message, a packet, from any device to any other device anywhere in the world, not necessarily on the same local area network. So just like the link layer, data is chunked up into these frames or packets. For whatever reason, with link layer, we call them frames. With network layer, we call them packets. I don't know why we have a different name for that. And just as before, each packet is going to have a source and a destination. But the addresses, it turns out, are a little different because the addresses now are globally unique and describe, like, uniquely identify the device and also which local area network it's part of, are like contain enough information that the protocol can get a message to the intended destination. So like in postal mail, if I want to send you a letter, I don't just put your name. I put your name and, like, you know, the street and the city so that the postal system knows how to get that to you. If I just put the name, the postal system might not know where you are. So how do we get that envelope to you? Same deal with the network layer. The network layer addresses are effectively going to contain something that's kind of like a address in a city. So the protocol knows where to send that message, how to get it there to you. Okay. So the way to think of the network layer is you've got multiple local area networks. Here I've shown two. And you want to connect them up. And so we connect them up with a device called a router. And what is a router? A router is just a device that lives on more than one local area network and will enable, like, bridge communications between them. So in this example, the router is a device on the top local area network, and it's also a device on the bottom local area network. Okay. And the reason why we need this is because it doesn't scale to have one giant link layer that encompasses everyone in the world. Like, how would you do that with Wi-Fi? You would need, like, really, really powerful radio transmissions, you know, like ham radio or something like that. And anything anyone sent would be, like, maybe colliding with anything anyone else anywhere in the world sent, even if you could, like, if you could get a global or, like, radio network. And so it would scale really badly. When I just want to send some data to a local Berkeley server, that's messing with communications to everyone else everywhere in the world. That's not good. So local area networks allow me to keep local communication local, and only these long distance communications need to go over the public internet. Okay, but that means now that if A wants to send a message to H, there has to be a way to start on the local area network at the top and get to the local area network in the bottom. And the router is going to be responsible for that. And of course, in the real internet is not just two local area networks, but there's like thousands, tens of thousands, hundreds of thousands of local area networks. And so we need not just one router, because you can't have one router that's like part of every local area network, but you have a whole lot of routers. And so now on the internet, each router is connected to one or more local networks and is also connected to other routers, maybe by some local network that connects the two routers. And so if A wants to send a message to D, then A tries to send this message and notices D is not on the local area network, so I don't know how to get it there. But I'm connected to a router, so let the router take care of that. And the routers figure out that there is a path through this graph that gets from A to D, so that this message can be forwarded from A to the first router, and then the first router can forward that to the second router, and the second router can forward it to the third router, and the third router finally forwards it to D. And it's the job of the network protocol to figure out like how to find that path and how to get that data across all these routers and between the local area networks. One thing to note is that each line in this graph, each edge in this graph, is like a local area network, like a link layer, I don't know, connection or something. And the way the internet is designed, each one of those can be different. Some of them could be Wi-Fi, some of them could be Ethernet, some of them could be fiber optic, which has its own protocol. That's fine. From the perspective of the network layer, what it needs is that there is some link layer that takes care of each edge in this graph, that has the ability to send frames with a source and a destination, like a MAC address, source MAC address, destination MAC address, some data. So the network layer is also responsible for like enabling the internet to work, even though we have different local area network technology around the world. Okay, so there's only one network layer. Well, okay, there's two. There's basically only one protocol at the network layer, and it's the internet protocol. There's actually two variants. There's a version 4, IP version 4, and an IP version 6. They're very similar. So in IP, the internet protocol, a packet has to have the same three fields: a source address, who's this message coming from, a destination address, who's it going to, and data, whatever like sequence of bytes is chunked up together into this message. So this looks very similar as the link layer. One thing that's a little confusing is that the addresses that's used in IP is a different set of addresses than the MAC addresses used at a link layer. So your computer will have if it's connected to Wi-Fi, a MAC address on the Wi-Fi network, and an IP address that's used for the IP protocol, the network layer. And those two are unrelated. And if you're walking, you might get disconnected from this Wi-Fi network and then like connect to another one. And when that happens, your IP address might stay the same, but your MAC address might change. Can happen. So people who want to use IP to send a message, send that in terms of IP addresses, and then it's the network layer protocol's job to translate that to MAC addresses and actual devices. To send you a message over IP, I don't need to know your MAC address, I just need to know your IP address. And packets are some amount of data, they might have some size limit. And so if you have a longer communication than that, it can be broken up into smaller packets. The router's job is to, when it receives a packet, if the packet's not destined there, it's destined somewhere else, to pass it on to either the eventual destination, if the router's connected to the intended destination, or if not, pass it on to another router that'll get closer. And in IP, there's no guarantees about what routes a packet will take. You could send two packets to the same destination, but they might follow different paths. There's some non-determinism or randomness that can happen depending on like which routers are overloaded. This router might decide to say, well, normally I'd send it to that router, but that router looks really busy right now, so I'll send it to the other router, which also is a reasonable way to get to the destination. Okay, so IP is, as I was saying, the protocol that we use for the network layer, and that kind of defines the internet. And an IP address, well, in IPv4 is 4 bytes. And in IPv6, it is 16 bytes. And the primary reason why IPv6 was invented was because 4 bytes is not enough. 4 bytes, that's 32 bits. That's 2 to the 32 possible IP addresses, which is 4 billion. And it turns out we have more than 4 billion devices in the world. You know, there's more than 4 billion people. And, you know, not everyone has a computer, but a lot of people have a computer and a cell phone and, you know, some IoT thing and a watch and so on and so forth. And so we end up needing more than 4 billion addresses. And so, oh, shoot, we ran out. And so people invented IPv6. So we're never going to run out of addresses. And these addresses are globally unique. So if your machine has an IP address, then no other machine in the world should have that same IP address. The IP addresses also have some structure that helps figure out something about the region where they're located or where to send the data. And I should say something about reliability with IP. We're used to communications being in the physical world being pretty reliable. But on the internet, there's no guarantees about reliability. And this is one of the like innovative things about the internet. It sounds crazy, but the innovation was, I'm going to be not reliable. A lot of previous systems were reliable and the internet said, nope, I'm going to make no promises about reliability. So the telephone system like tries to achieve more than 99.99% reliability and the internet says, whatever, I make no promises. Maybe your data will get there, maybe it won't. So there's a couple of mechanisms in IP to try to deal with reliability, but none of these are guaranteed. One of those is that as data is transmitted, there could be some errors. The data could get corrupted. Does anyone want to give me an example of how that could happen on a Wi-Fi network, for instance? Yeah? Anything generating radio waves through the air could corrupt the signal totally. If like, it's not true on Wi-Fi, but let's suppose it were true that a 1 bit is I send it, you know, frequency A and a 0 bit is I send it frequency B. And then I start using my microwave oven to heat up my lunch. If it's not really well isolated, that's letting out radio waves at all sorts of frequencies. And so the recipient might be like, I see radio waves at both A and B, I don't know what to do. And so if I am sending a frame and then someone turns on the microwave halfway through, the first half of that might get through and then the rest might be replaced by like random bits or something like that. So to deal with that problem partially is IP packets include a checksum. And so the data is checksum. So the recipient, when they receive the data, they can also checksum. And if the checksum is invalid, then the recipient knows something went wrong. Maybe someone turned on a microwave and they'll drop that packet. They'll ignore that entire packet. Say something was wrong. I don't know what. I can't trust any of the data in this packet. Let me just treat it as though I never received it. So this is not a guarantee. There could be corruption to the data that still leaves the checksum valid, but most random errors will probably be detected by the checksum. It's like your credit card number, the last digit is a check digit. And so when you're like just telling someone over the phone your credit card number, if they type it in wrong and then they get a digit wrong, probably that check digit will not match, not be consistent with the rest of the number. And they'll be like, oh, sorry, something's wrong with your credit card number. Try and tell me again. So we're going to do the same kind of thing here on the internet. Checksums. But no cryptography. So if there's an attacker present, they could be modifying data and like modifying the checksum to match up with the modified data. So it doesn't provide any like security against an attacker. It's just dealing with like random errors. And internet protocol is unreliable. So it'll try to get your data through, but data might not make it. One thing that could happen is the data could be corrupted because of this random noise, leading the checksum to be invalid, and then the recipient ignores it. It didn't make its way through. Another way is that a router can get overloaded. And what the protocol says to do, if you're a router and you get overloaded, people are sending you too much stuff and you can't keep up and you're overwhelmed and oh my gosh, I just can't handle it. So you just start ignoring some of the messages people send you. It's like, I'm overwhelmed and my email message is full and I just like hit delete, declare bankruptcy, delete my entire inbox. So routers will do that from time to time if they get overloaded. Stuff can happen and your data doesn't get through. So it's up to the internet protocol says, I'm not going to do anything about that. I'm not going to do very much about that. It's up to higher level protocols to provide whatever reliability they need. And it turns out this like enables the internet protocol to be really simple and really high bandwidth, really fast, really high performance. And then the applications that need reliability can provide it. If you needed reliable transfer of data and you're sending data over IP, what's the technique or what are some techniques you could use to provide reliability, given that IP is not going to give it for you? What could you do about this? Can you say it again? I couldn't hear you. TCP. TCP, yeah, absolutely. Good answer. TCP is a protocol that's going to solve this problem for us. Imagine TCP didn't exist. How does TCP do it? Or like, what would you do if you didn't have TCP or you had to invent TCP? Yeah? Awesome. The sender could add a message authentication code, a MAC, and the recipient could check that the MAC is valid. And that will make sure that the data hasn't been modified. What part of the problem does that not solve? That's good. It's not a complete solution. Yeah? It doesn't ensure that packets are received in the same order they were sent. What else does it not solve? Yeah? If the packet's dropped, the receiver doesn't receive anything, has no way to know that the packet got dropped. So what can we do about, let's separate those two. What can we do about the packets getting dropped problem? A message authentication code is good. We're going to need more than that. What else can we do? Yeah? Uh-huh. Okay. The sender sends a message. The recipient confirms by sending back a response saying, here's what I got. Yeah. Yeah. Oh, what was you said something more?
Yes, sender checksum.
Send a checksum. Okay, okay. So the sender could send a message, the recipient could copy back what it received, but maybe more efficient is the recipient could send back a checksum of what it received. Good. So if the sender receives this reply, then the sender knows the message got through. What else should the sender do if the sender does receive this reply? Send again. Keep sending until you got a reply, until you got an acknowledgement. Or try multiple times, or yeah. Uh-huh.
But then does the other person stop sending I got the message?
Uh-huh. Oh, if the sender doesn't get back this reply, it could be because the sender's message got dropped or because the receiver's reply got dropped. There's no way for the sender to know. So when does the recipient stop sending a reply? I only need to send one. Yeah. Yeah. So the sender sends a message, the recipient sends one reply. And if the sender doesn't get the reply, the sender sends again. And you just keep trying until you get a reply. Good. Okay. So that's called a retry mechanism. That's a retry. Sender sends it. The recipient sends back an acknowledgement. The reply is typically called an acknowledgement. And if you don't get the acknowledgement within a certain amount of time, you retry, resend it. Yeah. Anything else? Yeah. Good. Okay. So you're solving the problem of reordering, that the packets might be received in a different order that they were sent in.
You're like missing something in the chain.
So a solution to that could be the sender can stamp the order. Typically that's done by putting a counter, an index number, sequence number in the packet saying this is one of three. The same way you put on a paper document, page 1, page 2, page 3 is packet 1, packet 2, packet 3. And then the recipient, if they arrive out of order, just kind of reshuffles them to put them in order. Okay, good. So absolutely, these are some mechanisms you could use for reliability. Okay, so the network layer solves how do we get a packet from A to D? Probably. But without reliability. So the next problem that we need to solve is reliability. And we're also going to need a way to send an arbitrary amount of data, not just one packet's worth, but maybe there's a whole stream of data or entire file. And so that's the job of the transport layer. And we've just been talking about how you might solve those problems. So the transport layer provides a way, it uses IP and provides a way to send any length of data, variable length, could be short, could be long, often with reliability. And also it solves one more problem, which is IP describes how to send data from one computer to another computer. But usually that's not quite what I actually want. I actually want to be able to send data from one application to another application. Like from my web browser to the web server on that machine, or from my Skype application running on my machine to the Skype application running on your machine. And there it's important to distinguish whether the data that I'm sending is intended for the Skype application on your machine or the web server on your machine. So that's one more thing that the transport layer provides, is a way to identify not just machines, but actually applications, software programs running on those machines. And there's two standard ones on the internet, TCP and UDP. And the difference between them is reliability. TCP provides reliability and UDP does not. And for most purposes today, everyone uses TCP. At one time, the thought was if you don't need reliability, use UDP. So you only pay the cost of reliability if you really need it. But it turns out the cost of reliability is not very much. And so it's simpler to just use TCP. So what TCP does is it breaks up this arbitrary length message into packets, sends them using IP, and sends back acknowledgments when they're received, retries if it wasn't received, and also has a way to identify applications running on each device. So what it does is, in addition to the IP address, it also, on each machine, there's port numbers. Each application running on a particular machine gets a separate port number. And so now in TCP, the destination is identified not just by the IP address, but the IP address and the port number of the application that this message should be passed on to. And then the final layer is the application layer, and that refers to like the software package you're running, like Zoom or Call of Duty or whatever, your web browser. Okay, so those are the main layers and what they do, what problem they solve, and like conceptually kind of the approach they're taking. The next thing that I wanted to tell you about was like how that translates into data formats. But before I do that, do you have any questions? Discussion? Yeah.
A router that devices, does it just like stop working or start sending data to like the devices?
It turns out that MAC addresses are assigned by the manufacturer usually. like my laptop has a MAC address that was assigned by the manufacturer. It doesn't have to be that way, but usually it's not assigned by the router. And there's like the MAC addresses are 48-bit values. You basically don't have to worry about running out. There's more than enough. Yeah, so they don't really say anything, I think, about what to do in that case because they just kind of don't worry about it. Yeah,
Say something that. Good, fine, push.
yeah, yeah, absolutely. Yeah, at least a decade, maybe more. We've been in the process of trying to adopt IPv6, and some computers and some servers are accessible over IPv4. Some are accessible over IPv6. Some over both. And because we're running out of IP address, many entities are like trying to convince the world, let's switch to IPv6. I'll make my computers available over IPv6. Could you please talk to me over IPv6? This way I won't run out of addresses. And some parts of the world are like still running IPv4 and they don't support IPv6 yet. And they're like, well, I got my IPv4 address. I don't care about the rest of you. I'm good for now.
Remotely. I guess.
Yeah, but there has to be not just your computer, but also your internet service provider has to support it. Yeah. Should we take a 2-minute break or should we keep going? Two-minute break? Keep going? No one cares. I'm going to keep going. I can see there's a lot of data dump. Sorry about that. So in terms of how to like implement this in data formats, the key idea in network protocols is that of a header. And so let's suppose that Alice wants to send Bob a message like, I'm hungry. Or I'm at summer camp and I miss you terribly. Then Alice writes a message, and then typically she would put that in an envelope. And in the envelope, there would be a 2-line to Bob. And there might also be an address on that. So in the digital world, it's the same thing. We have a 2-line and maybe a physical address as well. And in the paper world, that's like a piece of paper inside another piece of paper. In the digital world, that's going to be represented by fields of a struct, like basically concatenation of these multiple types of data. Then the mail carrier only needs to know about, you could think of this, it's not how we actually do the postal mail, but you could think of it as like 2 nested envelopes, right? Inner envelope says to Bob, outer envelope says 223 Vine Street or something like that. The postal carrier only has to look at the to address on the outer envelope and figure out how to get it to that address. And then when it gets to that address, maybe that's an apartment building, maybe there's, or maybe that's the, I don't know, the mail sorting center or the EECS department. Then remove the outer envelope and they look at the inside envelope and they see it says to Bob and they know they need to put it in Bob's mail slot. And then when Bob receives it, Bob can take off that inner envelope and find the message from Alice. Okay. This is kind of like layers on the internet. This is kind of the analogy for layers on the internet, where Alice and Bob are like the applications. And then the bottom layer, the postal layer, is like it's not a very good analogy. But it's like TCP wants to send a message, the ability to send a message to a particular application. So here we want to send a message to a particular person in that apartment building or in the business building. And then IP provides a way to send a message to an IP address, like to an entire building, entire apartment building. So it's like the name Bob is like a port number, and the physical address 123 Vine Street is like the IP address. And the postal worker doesn't need to know anything about port numbers, only needs to know about IP addresses. And the mail sorter who sorts mail coming into that apartment into the right mail slot doesn't need to know anything about how the postal service works, just needs to know how to look at the name Bob on there and figure out which mail slot this envelope goes in. Okay, so we're going to do the same thing in the digital world where it's like each layer of abstraction like puts another envelope. Except instead of envelopes in the digital world, what we do is we add another field to the message. We prepend some data. That is, we call that a header. So in this case, Alice, the application, wants to send I'm hungry. And she asked TCP to send this to Bob. So Bob constructs a packet that has like port numbers, deliver this to Bob, and then the message is I'm hungry. And TCP gives that to IP and says, get this to the following IP address. And then IP prepends to that some data that says, here's the IP address this should go to, followed by here's the port number identifying the application this should go to, followed by the data that should be delivered. Okay. So on the sending side, you start with the highest layer, and that invokes services the layer below it, which invokes services the layer below it, like calling the library. Each of those layers prepend some data to the beginning of the message. They prepend these header fields. And then they take all of that chunk of data and they ask the next layer to send that entire chunk of data. Don't worry about what's in there. It actually starts with some headers, but don't worry about it. Just send all of that. And then the receiving end, there's this whole collection of headers, like link layer headers, sorry, physical layer headers. Well, let me start over again. Link layer headers followed by IP layer headers, followed by like port numbers for TCP. And the link layer just looks at the link layer headers, and then everything after that, it doesn't care about what format that is, and figures out what machine to get this to. And then the internet level software on the receiving machine just looks at the IP headers and ignores the port numbers and gives that to TCP. And then TCP looks at the port numbers. So there's a whole bunch of headers, and each header can be associated with one of the layers. And the code for each layer only looks at the headers it's associated with. Okay, so conceptually, that's how like layering turns into data formats. And an example of a data format for a link layer data frame, might look something like this for Ethernet. The specification for Ethernet might say the first 6 bytes are the MAC address of the machine that sent this. And then it says the next 6 bytes are the destination address, the MAC address of the machine that this is intended for. And then there's some stuff you need to worry about. And then there's 2 more bytes you don't need to worry about. And then there's data. The rest of this is data. So receiving machines know to look at the second 6-byte value, check if that's them, and if so, remove all of the yellow stuff and keep the pink as the data, and then deliver that data to whatever layer is above them, like IP, to interpret. The pink is for an upper layer to interpret. So the Ethernet layer doesn't care about what is in the pink region. The level layer 3 header, in other words, the IP protocol header, has its own format. This one's a little more complicated. But the crucial thing in there is you can see a source address. Here's the source address, the IP address of the sending machine, and there's a destination address, the IP address of the receiving machine. And then there's data. The pink is data, which the IP layer doesn't interpret, says that's some data and passes that to like TCP to figure out how to interpret on the receiving end. So the Ethernet frame might look like this, and then the pink region here, the data part of the Ethernet frame, might be this IP packet with the IP headers followed by the IP data. Yeah. Which parts of this are encrypted? None in HTTPS. So in HTTPS, the link layer is not encrypted. Okay. Let me rephrase my answer. In HTTPS, your web browser encrypts the data, and then it asks TCP to send the encrypted data. So none of the headers will be encrypted. The data for the TCP packet will be encrypted. It's been created by your web browser. But the TCP header, the IP header, the link layer header, none of those will be encrypted.
Data.
What's the data section? Yeah, what's the data section? The data section is something to be interpreted by the layer above it. So it may in turn have headers from the upper layer above it, and then data. So for IP, this data typically will be some TCP headers followed by data from the application. But I don't draw the TCP headers here because when you're writing the IP software, it just ignores the contents. It says that's TCP's job to worry about it. I just treat that as like opaque stream of bytes. So it's like a software abstraction structuring principle. Yeah. Yes, everything, this whole picture, starting from version on down on to data, becomes the data in the link layer.
So like layer 2, how do we have?
Yep.
Why do you?
Yeah, isn't that weird? Like an Ethernet frame will have Ethernet source and destination address, and then also an IP source and destination address. Yeah, it's kind of weird. It turns out, why do I need that? The short version is if I want to contact Amazon's web server, their web server is probably not on my local area network. So I'll put in there the IP address of the Amazon web server, but I don't know the Ethernet address. There is no Ethernet address on my local area network. So instead, at Ethernet level, the Ethernet destination address will not be Amazon. It'll be the wireless access point that can get the packet one step closer to Amazon. So that's why they're not the same. The IP address is like the eventual destination. The link layer address is like the next step on my local area network. Yeah. From Ethernet's perspective, if you're writing Ethernet code, Ethernet's like, I don't care what's in that data. This is the final destination for Ethernet. But from IP's perspective, IP is like, no, it's going to traverse multiple local area networks, so it's not the final destination. Yeah. Yeah.
They just feel not there.
Yeah.
They don't.
Yeah. Yep. And then once they peeled off the data section, then they hand that to the IP layer to interpret all this stuff here. Yeah. And there's other stuff in this IP header that is less important. Like there's a version field, so you can see whether it's IPv4, IPv6. There's a length, so you know how long the packet is. There's an ID field that's like hopefully different more or less for each packet you send. Not quite, but almost. There's a checksum. You can see there's a checksum. So like errors in the header can be detected. There's a time to live field, which like prevents IP packets from like circulating in the network forever. At some point they expire. So putting together multiple layers, if my web browser sends an HTTP request to Amazon, the way that works is my web browser constructs this data that's the HTTP request, get/HTTP, whatever. And then hands that to TCP and says, TCP, would you please get this to Amazon's web server? So TCP says, I know how to do that. I put the port numbers of Amazon's web server on there, and I ask IP to get it to the machine, the Amazon's machine. So the port number, port 80, is the standard port number for a web server. TCP puts these headers at the start, like saying this should be, this is intended for the software application on port 80, followed by the HTTP request. So that's now a longer stream of data. Hands that to IP and says, would you please get this to the machine where Amazon's web server is? The IP layer says, okay, I know how to do that. I can construct a packet with some headers that indicate the source and the destination IP address. So the IP constructs an IP packet that starts with source address, my machine, destination address, the IP address of the Amazon web server, followed by what IP considers data, but which we know actually starts with the TCP headers and then has the GET request. And IP says, having constructed that packet, talks to the Ethernet layer and says, hey, Ethernet, I've got this packet. Would you please get this to Amazon, or at least one step closer? So Ethernet says, oh, I know how to do that. I have to make sure that this is an Ethernet frame. So it constructs an Ethernet frame by starting out with some Ethernet headers, and then followed by what Ethernet considers to be data, which is all that stuff we just constructed, the IP packet. And the Ethernet headers, the source Ethernet address, source MAC address, will be that of my machine. And the destination MAC address will not be Amazon's, but will be like my Wi-Fi access point, or the router that is connected to my local area network. And the router's job to figure out how to get this packet eventually onto Amazon. And then the physical layer converts that into like radio wave signals and like jiggles the, the radio stuff on the antenna, whatever that is, I don't know, sorry. And then that's now transmitted. And then in the receiving end, maybe the Wi-Fi access point, which also acts as a router on my Wi-Fi network, has an antenna, is listening to these radio waves, converts that back into bits and bytes, interprets that as like an Ethernet frame or a Wi-Fi frame. Those frames start with a source and destination MAC address. My Wi-Fi access point sees that the destination MAC address is itself, so it says, I know I should pay attention to this. So it removes the Ethernet, the link layer headers, leaving the rest, treating the rest, handing the rest to an IP, to the IP protocol, and the rest is an IP packet. This IP packet says the IP address of the source machine, the IP address of the destination machine. The IP software on the receiving end checks to make sure that it's intended for, like Amazon checks to make sure this is really intended for the Amazon web server, for that machine. And if it is, removes the IP headers and hands it on to TCP. And then the TCP headers indicate what port number this should be delivered to, which software application this packet should be handed to. In this case, port 80 means give it to the web server application. And then the web server application gets the remaining data after those TCP headers have been removed, which in this case is the GET request that tells the web server this browser wants to access the, I don't know, the home page or something like that. So headers, tons of headers get added, and then they get removed at the destination machine. And each of these horizontal arrows corresponds to one layer in this abstraction. Okay? So in summary, you can think about how the internet works is it's a collection of these protocols that each solve a piece of the problem and that together allow any application and any computer to send data back and forth with another application. And I think that's my primer on the internet that I want to give you. Let me open things up for like, ask me anything about how the internet works, and I'm glad to answer if you have any. Yeah? Wow, why is the source there? Yeah, the source is there for only one reason. When the Amazon web server receives this request, it needs to know where to send the reply back to. That's the only reason it's there. Otherwise, it wouldn't be needed. Yep. They were like on paper trying to design what they thought would be the theoretical ideal without really like building something and seeing what the real challenges were. And it turns out that what those layers did, I forget what they did, but it turned out it wasn't important to provide in the internet. The applications provided them themselves. Totally forget 5 and 6. Yeah. And even this is kind of a lie because most software, the way that it's actually built is like TCP and IP. It's often one code base that does both layer 3 and layer 4. And so I'm kind of like imposing this conceptual structure that makes it easy to think about, but it's not how quite how systems are actually built. Yeah.
We're sending a source, it doesn't get tampered with on the way, or are we not worried about that, hoping that?
You use a security class, so we're totally going to worry about it. And this was the networking section, and the networking folks were like, they didn't do anything about it. It was like initially designed as a way the physicists could share their paper preprints with each other, and then people started using it to share cat pictures, and then we started using it for e-commerce. But when it was initially designed, security, pshaw, who cares? It's a physics paper. I'll give it to anyone who wants to see it. Someone reads my paper. I'm so psyched. So that means that now we have to, given that this whole internet has become popular and didn't have any protections against any of this kind of tampering, attacking stuff, we have to find some way to retrofit it in or provide protections after the fact.
That's all layer works. That's like building software.
Yeah, this is a way of structuring the software in the device. It's also a way of like decomposing the problem. So you can have like one standards committee that figures out how to design Ethernet, and another standards committee that figures out how to design TCP, and another one that figures out how to design Wi-Fi. Yep. Drivers in your operating system will implement all of these. Yeah. Yep.
Like its plan, or how does it know like whether to send it to another stop?
Ah, the job of the router is to understand this internet protocol address stuff. And if a router receives a packet where the MAC address is the router, but the IP address is not the router, then the router knows, oh, I'm actually being asked, this packet was not intended for me. I'm being asked to help get it to the final destination. And so then the router, there are these routing protocols I haven't told you about that tell routers how to figure out what path through the internet to use to get this to the eventual destination. So you could think of it as like doing a shortest path computation in a graph, but the graph is now all computers in the internet or all routers in the internet or something like that. Yeah.
Idea that like protecting your IP, what data in IP that can like tell about me of like a person using a device, like maybe locational data? Like how much do you actually do to like protect that?
Yeah, the IP address doesn't have very much information about you, but um, it's assigned by whoever, whatever network you're connecting to. So if you're using at home, you're using an ISP, your ISP assigns you an IP address. Here at Berkeley, when you connect to a Berkeley network, Berkeley assigns you an IP address. And the ISP has like a, a range of IP addresses, or Berkeley has a range of IP addresses. And people can look up your IP address and see, oh, that was an IP address assigned by Berkeley. So you're probably, you know, Berkeley student or staff or faculty. So it gives a little bit of information. Or if you're in your ISP, they can look it up and maybe they can, there's a place where they can look up and say, okay, this is a Bay Area. This is a range of numbers you use for the Bay Area. And the other thing is that when you're assigned an IP address, it's not permanent for your machine, but it might be stable for a day or a week or something like that. And so if you make connections to 5 different sites in succession, you'll be using the same IP address for those. And so those can be kind of linked together. So like if you go to Google and you search for like great vacation spots, and then you go to the New York Times and there's some ads there, then they can tell, oh, that's the same person who previously was looking up vacation spots. Maybe I should provide some ads that are about vacation spots. They actually have other ways to do that that are better than an IP address, but that's the kind of thing that an IP address could partially leak about you. Yeah. Yeah, exactly. A VPN is like another internet service provider that gives you a different IP address. And they also do encryption. Yeah. So one thing that people often use VPNs for is like, you know, it's someone in Canada, but Netflix is blocking access, so you want access. So the VPN has IP addresses that are associated with like the U.S. range, and they're typically doing that based on the IP address to figure out the geographic region that you're in. And totally could be wrong. Absolutely. Some companies will do it based on your like credit card number also. That's another way they can like use geographic restrictions. I think this is a great time to take a break. Let's take a 5-minute break and come back in 5 minutes and we'll have snacks up here. Okay. I know it's a long lecture, not a very interactive. So like, feel free to just stand up and stretch your legs at any point or do whatever you need to do. What I want to transition now to doing is starting in on the security side of things. So I taught you some things I think everyone know about networks. Now we're going to look at security implications of networks, and I'm going to do that for starters by looking at attacks, looking at ways that you could attack the network, and then we'll eventually get to building up some defense. How could you protect against these attacks? But I think the first thing is to understand what the points of vulnerability are in our current network design. And I'm going to do that by like starting with the lowest level, lowest layers, and then just kind of like talk about vulnerabilities of each layer. So it's not necessarily starting with the most important ones first. But we're going to start with link layers. And there's three main types of network attackers that we need to think about, or that history has taught us. You can kind of cluster attacks into three categories. One type of attacker is called a man-in-the-middle attacker, and that is someone who controls the network communications between two endpoints. So for instance, if Alice and Bob are talking and their data is routing through some routers, if one of those routers is compromised or malicious, that would be a man-in-the-middle attacker. The data flows through the man-in-the-middle attacker through that router, and that router can modify all the data in the communication stream, can observe, read, copy, see all the data that's sent, can also add new data or add new packets to the communication stream. So a man-in-the-middle attacker is very powerful. If a router is compromised and the communication between Alice and Bob goes through that router, very powerful attacker. But also harder attack for someone to mount, because to be able to mount this attack, you either have to be in a position where you own that router, like maybe you're a government or an ISP, or you have to be able to hack into some router. So you have to find some vulnerability in the software that routers are running. Maybe more realistic but less powerful attackers are on-path and off-path attackers. And the distinction about this, an off-path attacker is some random other person somewhere else in the world who wants to attack Alice or Bob, but has no connection with Alice or Bob. So like Alice might be in California, Bob might be in New York, and this off-path attacker might be in Arizona or Belgium. An on-path attacker is an attacker that's not a man in the middle, but that is on the same local area network as Alice or Bob, or one of the paths that the packet goes through to get from Alice to Bob. So for instance, if Alice is connected by Wi-Fi, someone else on that same Wi-Fi network would be an on-path attacker. And on-path attackers have some extra powers, because an on-path attacker on the same Wi-Fi network as Alice can like monitor, eavesdrop, observe all the packets that Alice is sending or receiving. Wi-Fi is like broadcast over the air. So anyone on that same Wi-Fi network can see all the data that Alice is sending. And that gives an attacker extra power, for instance, to eavesdrop and also to do other stuff. Whereas an off-path attacker is an attacker that is not on the same local area network as Alice or Bob or any of the places that the packet is routed through. So an off-path attacker has no way to observe or eavesdrop on the data that Alice is sending to Bob. What an off-path attacker, what everyone can do, is inject a spoofed packet. So what do I mean by spoofing? By spoofing, I mean sending a packet. All packets have a source address in them. In spoofing, instead of listing your own source address, you lie. You put someone else's source address to try to pretend like it came from them. So like in email, I might send you a spoofed email that looks like it comes from your bank, Bank of America, and it says, there's an urgent problem with your bank account. Please log in here. And it looks like it came from Bank of America, but didn't actually. Spoofing, same deal with the network packets. Someone could send a network packet and put the source IP address to be the IP address of one of Bank of America's servers. And then, because there's no cryptography, there's no authentication, the recipient, when they receive a packet, they just believe whatever's in the source address, or they have no way to verify whether it's correct or not. So anyone in the world can lie about the source address, about their identity, and introduce a packet into the network, and it will make its way through to the destination and have this like erroneous source address. Okay. And like roughly speaking, there's no checking in the network to try to like prevent this. There's sort of, these days there sort of is, but sort of isn't. But as first order approximation, you can just assume that there's no checking. Okay. So everyone can inject spoof packets. Off-path attacker means everyone. On-path attackers, because they're on the same local area network, can also eavesdrop on the data. And then a man-in-the-middle attacker, in addition to that, can also modify the data. Whereas an on-path attacker who's just on the same Wi-Fi network can observe the data but can't change the data. Okay. So like some real-world examples of this might be on fiber optic networks. If you want to like spy on data sent over fiber optic network, it turns out that if you bend a fiber optic cable, some of the light goes around the curve and some kind of doesn't, just keeps going straight effectively, scatters out of the cable. Most of it goes around, but some comes out. And so you stick it in a dark box and you put it in, and then you put a little light sensor there to like detect the light that didn't go around the bend. And you can, that little device can now observe what data is being sent over this fiber optic cable. And it's even easier with Ethernet. With Ethernet, it's a wire with some voltage. So you just put like effectively a voltmeter on that to like measure whether the volt, is 5 volts or 0 volts, basically. If you have physical access to the Ethernet or the fiber optic cable. And in fact, the US intelligence services and probably other countries also have used this to spy on other countries. So like one famous like kind of mind-blowing example is the US spy agencies realized that Soviets were sending military communications over a fiber optic cable laid on the seabed, the like underwater between the different installations to try to prevent interception. They knew that like if they transmitted by radio, then radio could be, anyone with a radio receiver could potentially intercept that. So they sent it over this fiber optic cable, but they didn't encrypt the data. And so the US had this special project where we spent maybe $500 million to build a custom submarine designed solely for the purpose of like going under the ocean to where that cable is, sending out some divers to like hook up one of these devices that did this whole bending trick and whatever to like capture data that was being sent over there and like spy on Soviet communication for years. Eventually the Soviets, I don't know how, discovered the tap and removed it, started encrypting and so on. But kind of shows the lengths that like spy agencies will go to try to intercept data. And this basically made the NSA a on-path attacker. They could eavesdrop on all the communication. How would you do this? Oh, I already said how you do it on Ethernet. It's easy. How would you do it on Wi-Fi? Yeah? Just listen to stuff uncensored. My laptop has an antenna and some like physical circuitry that interprets the radio waves and turns them into bits. And there's some software driver in there that says, check every Wi-Fi frame to see if the destination MAC address is for my machine. If not, ignore it. And you just remove that check. And then you have to be in the physical vicinity that you're close enough that you can receive the radio wave. And you're done. Yep. Well, yeah, why didn't they encrypt it? Today, that's totally what we would do. I think maybe at the time this is started using this, that encryption was not so widely available and not so like cheap. We didn't have fast computers to do the encryption for us, I think. Maybe also they figured that since it was like going through a direct line that they didn't need to worry about encrypting. I don't know. I'm just guessing there. But yeah, encrypting would be it's a good solution. It's a better, like today we understand that, oh my gosh, spy agencies are going to do this crazy stuff, spend $500 million. So yeah, if you're protecting military grade traffic, you better encrypt everything. Another example of an on-path attacker is anyone on the same Ethernet network with you, or anyone on the same Wi-Fi network with you. And I just told you how anyone on the same network can read all the data. In fact, most drivers have a way to disable this check. Is this packet meant for me check? And just listen to all packets. That's a useful like network troubleshooting functionality for system administrators to use. They call it promiscuous mode. And the core problem here is these local area networks, all the data is sent by broadcast mode, so anyone else in the same network can observe it. And you'll get a chance to like play around with this in Project 3. There's tools, command line tool called TCP dump and a graphical tool called Wireshark that analyzes all the data being sent over a local area network and like figures out what packet types it is and decodes it and pulls out the headers and the data payload, reconstructs communication streams, so on. Okay. So on-path attackers can observe data if it isn't encrypted. But actually, it turns out they can do more. I want to start by telling you about the ARP protocol. And the ARP protocol is a way that on a local area network, how devices figure out the address of other devices. Okay. It's common that my machine wants to send a message to another machine. It knows the IP address of the other machine, but doesn't know the MAC address of the other machine. There's a way to look up the IP address of some machine I want to talk to. So then I need a way to figure out if they're on my local area network, and if they are, what's their MAC address, so that I can construct an Ethernet frame or a Wi-Fi frame that has their MAC address as in the destination field for the Ethernet headers or the Wi-Fi headers. So there is a protocol called ARP, Address Resolution Protocol, that is how computers do that. When my computer first connects to a network, doesn't know the Ethernet addresses of any other computer, any other device on that network. So if my machine wants to send a message to some IP address, in this example 1.2.3.4, the way it figures out what Ethernet address to use is the dumbest thing you could possibly imagine. It sends a broadcast message to everybody on the local area network. Hey, everyone on the local area network, do any of you know what the Ethernet address for IP address 1.2.3.4 is? Relies on the kindness of other people in the network. And hopefully one person will know and will answer. Send back a reply, an Ethernet frame that's a reply. And assuming that my machine gets a reply, then it adds that to like some database. Okay, now I know that the IP address 1.2.3.4 has the following Ethernet address. I'm going to remember that for a little while, 15 minutes or a day or something like that. And that's the protocol. So my machine sends this ARP request. Well, first my machine checks this cache, this database on my machine that has a mapping. But if I'm just connecting to the network for the first time, there's probably nothing in that. I haven't done this before, so I don't know any of the mapping. So the cache is empty. So my machine sends an ARP request hey, does anyone know what's the MAC address for IP address 1.2.3.4? And that to everyone. Why do I send that to everyone? Because I don't know. I don't know who it is. I don't know who to send it to. The only way I can send something on Ethernet is if I have a destination address, but I don't have any Ethernet addresses to fill in there yet. So the only thing I can do is fill in the broadcast address, send this to everybody. This is for everybody. Could anyone please help me, please? And then if Bob owns a machine that has IP address 1.2.3.4 and is on the same local area network, when he sees this, he'll say, oh, that's me. That's me. You're asking about me. I can help you out. Here's my MAC address. Okay, so everybody's machine is always listening. Are there anybody sending ARP requests for my IP address? If so, I'll help them out by giving them my Ethernet address. So Bob will respond if Bob is on the local area network. And then everybody else can ignore the request because they're not Bob. And then when I receive this reply, I add it to my cache. And now in the future, if I want to send a packet to that IP address, I don't need to go through this whole rigmarole again because I've got that mapping remembered from before. Okay, so that works if the machine with that IP address is on the local area network. What if it's not? 1.2.3.4 is not on the local area network. Then the router will know. There'll be a router on the network that knows, aha, there's an request for a machine that's not, for an IP address that's not on this network. So the router has to know what IP addresses are on this local area network, and therefore what ones are not. And the router is the fallback. If it sees an ARP request for an IP address that's not on this local area network, then the router says, why don't you send that to me? I'll help you out. So the router replies with the router's Ethernet address. That's the Ethernet address to send it to if you want to get a packet to 1.2.3.4, because I know how to get there. Okay. Then that enables the sender to construct this whole Ethernet frame with the Ethernet addresses and IP addresses and everything. Okay, so in this example, if Alice wants to know the MAC address for 1.2.3.4, she'll ask everyone. Oh yeah, attacks. Right. I wanted to tell you about attacks on this. So what attack surface does this open up? Yeah? What's that? Send the wrong MAC address. Yep. Bob could lie about what his MAC address is. What else? Someone else could pretend to be Bob. So there's no verification here. There's just complete trust. So it could be just lies. You could just lie in this protocol. So like one attack is if Mallory is a malicious person, has a computer on this local area network, then when Alice sends out this request, can you help me out with the MAC address for 1.2.3.4? Mallory could be listening, waiting for that and say, ha ha ha, I'm ready for that. Here's the answer, and respond with the Ethernet address for Mallory's machine before Bob can reply. Alice is only expecting one response, so the software takes whatever the first response is and trusts it and adds it to the cache and uses that for all packets sent to 1.2.3.4. So now when Alice wants to send a packet to 1.2.3.4, Alice constructs an Ethernet frame with the Ethernet destination of Mallory's destination address. So the frame will never go to Bob. It'll go to Mallory. So now Mallory can observe all the data that Alice wanted to send to Bob. And worse, Mallory can like reply, pretending to be Bob, and have a two-way conversation where she will see what Alice is sending and then send responses pretending to be Bob, but it's not actually Bob, but Alice thinks it's Bob. And then see what Alice says in response to that, and then craft a response based on that. So with this attack, Mallory can pretend to be any other user on the same local area network. What about pretending to be IP addresses that are not on the local area network? Can Mallory do that? I mean, this is like, let's say it's the IP address for like Amazon.com, www.amazon.com. So it's not on the local area network. What would normally happen if there's no attack is that the router would respond. Can Mallory get involved and mess with stuff? Let's take a poll. How many think yes, Mallory can pretend to be Amazon, www.amazon.com? How many think no, Mallory can't because Amazon.com is not on the local area network? Oh, we got a good entropy in class here. Does someone want to give me a reason why yes sounds plausible? Yeah? Could pretend to be the router. First pretend to be the router and then pretend to be Amazon. Interesting. Yeah. Yeah. Okay. Does anyone want to give me a plausible reason why no? Mallory can't pretend to be Amazon? Yeah? You think Alice should know the router's MAC address? And so not going to be able to use spoof this kind of ARP attack to like, Mallory won't be able to fool Alice about what the router's Ethernet address is. Because Alice should already know that. When she joined the network, she should have already communicated with the router. Okay, we got a reasonable argument for yes, a reasonable argument for no. What happens if Alice receives conflicting responses? The usual answer is the first reply. Alice is listening for a reply. As soon as she gets a reply, she says, okay, I'm going to add it to my cache. I'm done. I don't need to listen anymore. Yeah?
For Mallory, no answers. So if Alex does any sort of chat, it's exactly.
Okay. Yeah. Amazon, Mallory doesn't know like Amazon's private key. And so can't like spoof the public key authentication that happens in HTTPS. Uh-huh. All right, let's take that one out of the picture by imagining that Alice is making an HTTP connection. So there's no cryptography. There's no public key cryptography. How shall we resolve this? We got reasonable arguments for yes and reasonable arguments for no. Does anyone have any ideas after you've heard, now given that you've heard these arguments on both sides? Are we stumped? Yeah?
And the Wi-Fi security of most devices very safe here.
Okay, so you're arguing for yes is possible. How do we figure this out? Do you want to debate it out, or you want me to kind of just tell you the answer? Or? Let me just tell you the answer, and then you can see if it sounds plausible to you. It turns out Mallory can pretend to be Amazon. What would normally happen if there's no attack present, if there's no Mallory? What would normally happen is that Alice would send this request that says, what's the MAC address of whatever the IP address of Amazon is? And normally, because Amazon's not on the local network, the router would reply. Router replies, say, use the following Ethernet address. And the Ethernet address it would supply would be the router's Ethernet address. So the request just says, here's an IP address. The reply just says, okay, here's an Ethernet address for that IP address. That's what would normally happen. But what Mallory could do, the attacker, is wait for this request, send a bogus reply saying, sure, here's the MAC address for 1.2.3.4, and give Mallory's MAC address instead of the router's MAC address. And then when Alice sends some like HTTP request to Amazon, well, she thinks it's going to Amazon, but it actually gets directed to Mallory. And then Mallory can fake up a fake response and send it back. And so all of the traffic is not going to Amazon, it's going to Mallory's computer. So this attack allows any other machine on the same local network to like spoof, pretend to be any machine in the world. So if you go to a hacker conference like DEF CON, they say like, don't connect to the internet, or if you do, get ready. And one of the things that is like just happening left and right is hackers, just having fun, seeing what other machines they can hack, doing these ARP spoofing attacks, pretending to be, well, maybe not Amazon, but some other machine that you might try to connect to. Yeah. It doesn't rely on that because Alice's, but none of the software here checks for any of that. The ARP protocol just waits for someone to send me an Ethernet address associated with that IP address, and then uses that. Doesn't worry about any other details. It's not like there's some human in here that has some common sense, says, something doesn't feel right about this. And it doesn't have some explicit checks to say, I know this is a local or not a local IP address. I know what kinds of Ethernet addresses are reasonable here or not. There's no checks. Just ask, trust. Yeah. It's not possible to guarantee it, but maybe you have 50% chance of winning, or you just have the malware has a fast computer and gets there quicker, or yeah. So probably no guarantees. Sometimes the attack will succeed, sometimes fail. All right, so this means that there's one fundamental vulnerability that anyone on your same local area network can pretend to be anyone else you wanted to talk to. Kind of undermines all security, all network security, if anyone else in your local area network is not trusted. So that sucks. Sorry. Oops. The problem here is trusting. There's no way to verify the response. Alice's machine just trusts whatever it gets. And so, because there's no way to verify, it could be a lie. How do people defend against this in practice? Well, we don't really have any very reliable defenses. We have some heuristics that try to reduce the likelihood, like people use a hub and spoke topology. When the hub sees this ARP request, it doesn't forward it on to any other machines, but answers it directly itself, so that no other machine has a chance to like send this bogus reply, and maybe tries to filter replies so that replies are only allowed from the hub and not from other machines. It's kind of doable. You can also write there's also some software that you could optionally, but it's usually not, but could be run on endpoint machines to try to detect this attack. Like if you see an ARP request and you see two responses with different Ethernet addresses, whoa, that's really fishy. Maybe notify a sysadmin, we might be under attack, right? Okay, so that's ARP. The next protocol I want to tell you about is DHCP. And I want to tell you about attacks on that. DHCP is a protocol designed to help your computer when your computer first connects to a network for the first time. Doesn't know anything. It's like a baby and needs some help. To connect to a network, your computer is going to need an IP address so that other people can send like replies or send data to you, or you have an IP address you can put in the source address when you open a connection. So your computer needs an IP address. Your computer needs to know where to send DNS queries. So it needs to know the IP address of a DNS server. That's useful to look up, convert host names like Amazon.com into an IP address. And it's going to need to know the IP address of the router on the local area network that can be used to like forward data to other machines outside this local area network. So it needs this information. Where does it get that? Long ago, the answer was to connect your computer to a network, you had to ask a sysadmin for this information and then like type it in manually into some configuration dialog box. But that's annoying. System administrators didn't want to bother answering these questions. People didn't want to type it in manually. So people developed DHCP, which is a protocol to automatically provide your computer with this configuration information when it connects to a network. Okay, so when your computer connects to a network, it like asks for some help using DHCP, says, I need some configuration information. Can you help me out with it? And usually the access point or router will help. Okay, so in more detail, on each local area network, there is a DHCP server running that is available to help provide this configuration information. Often it's running on the access point or on the router. And when your machine connects and needs configuration, your machine sends a DHCP client discover packet. This is a broadcast message that says, help, I need configuration information before I can do anything. The DHCP server sends a response. The response is called the DHCP offer. It says, well, I could assign you the following IP address, and that would be good for the 24 hours, and here'd be the IP address of the router and the DNS server to use. Do you want that? And then the client, when it gets this response, this DHCP offer, it can say, yeah, I want that. I'll take that one. I'll take that IP address. So it's called a client request. And then finally the server says, okay, you're good. That's yours. That's your IP address now for the next 24 hours. There's the configuration information you need. You should be good to go. Okay, so initially Alice has this configuration information she doesn't know when she first connects to the network. And so to find it, she broadcasts this message, this client discover message. Everybody on the local area network says, are any of you DHCP servers? Can any of you help me out? And there might be one or two or more DHCP servers. Usually it's just one. It's weird to have more than one, but it could be multiple. Anyway, every DHCP server responds whenever it's listening, waiting for this request for help, and responds. DHCP server has a pool of IP addresses that can be assigned. And then responds with, suggests an IP address, and that knows is configured with the IP address of the router and the DNS server. And if Alice accepts this offer from DHCP server 1, then the DHCP server 1 marks that IP address as Alice's for the next 24 hours and won't hand it out to anyone else. And sends back an acknowledgement to Alice. Okay, I won't give anyone else that IP address. That's yours for the next 24 hours. Okay. So that's the DHCP protocol. And it too is a point of vulnerability. You'll notice that this is very similar to ARP. I need help, so I broadcast to everyone, and I hope someone will respond and help me out. And I have no way of verifying the response, so I just have to trust whatever is sent to me. So the attacks are very much the same as against ARP. Mallory can sit there listening for these client request messages and pretend to be a DHCP server and respond with lies about the configuration. And if Mallory's response gets there first before the real DHCP server, maybe hers will be accepted. That's kind of a default thing to do, is to take whatever the first response you get. So Mallory can arrange that people who connect to this network end up using configuration information that Mallory chose instead of the legitimate configuration information. Now my question to you is, do we care? Do we care if people who connect to this network use configuration information that Mallory supplied? So there's 3 pieces of information in this configuration. One is the IP address. Should we care if Mallory's providing the IP address that Alice is using? Should Alice care? How many say yes? How many say no? Okay, interesting. Anyone want to make an argument for your preferred side? Yeah? Long as it's unique, it doesn't matter. Doesn't really matter. You just need an IP address. Doesn't really matter what the IP address is. So the stakes are pretty low. I guess Mallory could give Alice an IP address that someone else already has, and then confusing stuff will happen. But you know, I don't know, maybe a network connection. The networks won't work right, or doesn't really help Mallory that much. So that IP address that's assigned, not a big deal. Not much that Mallory can do by lying about that or providing some alternative IP address. What about the IP address of a DNS server that's used to convert host names to IP addresses? Does that matter? Does it matter if Alice ends up with the IP address selected by Mallory? Yeah, you see you shaking your head, yes. Why? Yeah? That enables impersonation. Yeah. Yeah?
Think that around, well, she said like all packets to Mallory. So like, I feel like it maybe wouldn't matter so much if she's requesting like a big DNS server, because like if Mallory wanted her to send a packet to a certain IP anyways, then like Mallory could do that without needing the DNS server.
Mallory could do bad stuff with eating the fake DNS server. That's true. That's true. There's going to be multiple ways that Mallory could do bad stuff. So one way that Mallory could do bad stuff, you're absolutely right, is by providing a IP address of a fake DNS server that Mallory controls, that lies. When my browser asks for the IP address for Amazon.com, lies about what it is. It provides an IP address that Mallory controls. And now my browser thinks it's going to Amazon, but it's actually going to Mallory. So that DNS server configuration that's provided, that really matters. That would enable Mallory to become a man in the middle by providing a fake DNS server. What about the IP address of the router that is contained in the DHCP configuration? Does that matter if Mallory lies about that? I see you shaking your head. Some of you shaking your head, yes, you're right, it does matter. Why? Why should I care if Mallory lies about that? And now it's set up for you. Yeah. So what Alice is sending stuff, the thing she's sending it to the router, but she's actually sending it to this, you know, fake router IP that Mallory provided. So again, Mallory can become a man in the middle. So you might notice the theme here is an on-path attacker, a malicious attacker on the same local area network as Alice, can fool Alice in such a way that Mallory ends up having all the powers of a man-in-the-middle attacker because of this vulnerability in DHCP. Is the same deal with ARP. Yeah.
Why isn't it like when failing like
Why do we rely on GP to buy the DNS server? It turns out that if you connect to a Berkeley network, you get handed a Berkeley DNS server. And if you get connected, if I'm at home and I get connect to Sonic, my ISP, then I get handed a Sonic DNS server. Why is that? The reason is it saves money and it provides better performance. So the Berkeley DNS server accepts DNS queries from all Berkeley students and staff and employees. And if I look up CNN, then it will like figure out what the IP address for that is. And then if you look up CNN, I've just looked it up and it remembers the answer and it can immediately get you the answer. So it can get very quick responses by sharing this DNS server among multiple people. And it's useful for Berkeley because it like cuts down on the number of queries they need to send outside the Berkeley networks. So it reduces the bandwidth to the outside world and provides faster responses for us because Berkeley students, maybe there's some overlap in what we tend to access. Like we're all accessing berkeley.zoom.us. And so like it's great. It's always cached in the Berkeley DNS server. So for performance reasons, it's useful to use the DNS server that's like local to the network that you're connected to. And so that's why DHCP will give you that as a configuration option. You don't have to do it that way, but it gets better, like it's better performance for Berkeley and for you often. Well, this was all designed before security was a big issue. So absolutely they prioritized performance over security. They weren't even thinking about security. Yeah. Uh-huh. Every network has a just about has a DHCP server. Yep. Yep. Yep.
So like having IP that you're good.
Yeah.
But if Mallory is assigned IP, how will the router like what like?
Yeah, that's a good point. Yeah, your network might not work if Mallory gives you a bad IP. Yeah, that's true. Yeah.
But like, this might be getting into like a lower level, but like, for example, on a Wi-Fi, actually part between that anyways. Because it's not as if like, you know, if you're sending something wirelessly, it's not as if it's like latency on the router.
Yes, absolutely. Can't Mallory already read all the stuff that I was sending? Yes, because it's sent over like Wi-Fi, a broadcast medium. Yes. So what new powers does this give Mallory? It gives Mallory the powers to like observe what's being sent and send a response that looks like it came from Amazon. So it's not just observe. Mallory is on path. So we already said on path can observe, eavesdrop. But what this is enabling Mallory to do is to like become like a man in the middle. So also gain the ability to modify. Okay, so very similar vulnerabilities, even though they're different protocols. And these are hard to protect against. DHCP, it's hard to protect against these attacks because when I connect to a network, I have no information about that network, and I want to just have internet just work. So I have no way to know who or what to trust. I might not have any trust. It might be some coffee shop. So there's like just I don't know how you solve this. I don't think there is a solution in general. So the answer is we say, oh well, we don't have a solution. So we can't solve this at the link layer. We're going to have to rely on software applications to work around the fact that the network is not secure. So one of the themes that you're going to see as we look through these attacks is the underlying network is not secure. So all the responsibility for security is typically going to get left to applications to somewhere figure out how to achieve their security goals, even though the underlying network is insecure. We could modify the DHCP protocol and say, forget this whole idea of getting a DNS server through DHCP. That's not a good idea. But we still would have the vulnerability of the router. DHCP provides a router IP address and you need to know the router. So you'd still be vulnerable to that. So we don't really know of any way to fix that part. Yeah. Wi-Fi. Wi-Fi is a security risk because it's using radio waves. And anyone who has an antenna that is within range can receive those radio waves and transmit their own radio waves. And Wi-Fi, the access point, I guess I've been using that term, but what that means is there's a machine on every Wi-Fi network that is like a router and a DHCP server and like the hub. Plays a hub and spoke, and all of your other devices are spokes. Okay. So basic Wi-Fi networks have no security, no cryptography, no protection. Very vulnerable. Anyone who's within range of the radio can eavesdrop on all the communications sent over it and can inject spoofed packets in. So from the very instant that Wi-Fi was introduced, people understood, oh boy, we need a way to provide security. And there's been several iterations of security protocols for Wi-Fi. And the early ones had some major problems. So I'll spare you the missteps that the early technology took, and I'll just talk about kind of like today's Wi-Fi. And WPA2 is a protocol for securing Wi-Fi communications using cryptography. And the idea is that there is a password for the Wi-Fi network. And you need to know the password to join the network. And the way that's enforced is that password is used as a cryptographic key. All packets that are sent over the Wi-Fi network are encrypted with that key. Also, we use a message authentication code with that key. So someone who doesn't know the password won't know the key and therefore won't be able to decrypt traffic they observe, they receive from the radio waves, won't be able to inject spoofed packets because they won't be able to provide a proper MAC. Okay. So now it becomes a fairly straightforward cryptography design problem to use the cryptographic building blocks we like taught you in class, how to achieve that goal. And there's a little bit of like contortions that are in there, so I'll show you what's actually in the protocol. When your laptop connects to a network that's secured with WPA2, like home networks, most home networks typically, if you've got a password on it, it's probably using this protocol WPA2. So the client, your laptop, when it first connects, sends an authentication request to the access point. Says, I want to connect to the network and I want to prove to you that I'm authorized because I know the password. So then both the client and the access point derive a symmetric key called the PSK from the password. What cryptographic building block would be good to use for this, to do this? A slow hash. Yeah, password-based key derivation function. Yep. Great. Okay, excellent. So now, assuming that both sides have the same password, have the correct password, they should end up with a symmetric key that is the same for both of them. The PSK should be known to them and not known to anyone who doesn't know the password. So now you can imagine that you use this PSK for encrypting and macking all packets, but there's actually an extra level of complication that's done here. Is first, the client and the access point prove to each other that they know the password. And the way they do that is they send random nonces. So just a random value. Because it's random, it's unlikely to be repeated from anything previously. So the access point sends a random value and the client sends a random value. Then they derive a new key. Let's call it like a session key. It's called the PTK. You could think of T as for temporary. It ought to be for temporary. It's not actually, but think of it that way. This is a temporary key. which is derived from this PSK, a key known to both sides, and the random nonces, which were sent unencrypted over the radio waves, and the MAC addresses of both the client and the access point. What cryptographic building block might be reasonable to use to compute the PTK? Yeah? Diffie-Hellman. Aha, Diffie-Hellman would make sense, but it's not actually what it does. They don't use any public key cryptography. Diffie-Hellman would make sense if you wanted forward secrecy, but they don't do anything that fancy. They just want a symmetric key, so it's all symmetric key cryptography. They already have a shared key, PSK. So Diffie-Hellman's kind of more intended for the case where you don't have a shared key yet. So what are the building blocks we know? We know like encryption with block ciphers and stream ciphers, and we know message authentication codes, and we know hashes, and we know slow hashes, and we know some public key, like key exchange protocols. Do you have a thought? Maybe. Okay. Yeah. Yeah, that's plausible. What are you thinking? Oh, okay. Sorry. My bad. My bad. Sorry to put you on the spot. If you have a thought, you can share it. Oh, I'm glad I called on you. A hash. Yeah. Yeah. So it turns out a hash function is good enough. You could probably do something based on block ciphers too. Okay, so they hash all the data and form the PTK as the output of the hash function. So someone who doesn't know the password won't know the PSK and therefore won't be able to predict the PTK. Then this PTK now is the symmetric key that is used to encrypt all packets. First, before doing that, they verify that each other knows the password. And the way they do that verification, the way the access point proves that it knows the password, is it takes all the data exchanged so far and computes a message authentication code on that using the PTK. And then the client proves it knows the password by taking all the data exchanged so far and computing a message authentication code on that using the PTK. And the idea is that someone who doesn't know the password won't know the PSK, so they won't be able to get the PTK, so they won't be able to compute a correct message authentication. Yeah? Why do they compute a message authentication code on all the data sent so far rather than just on some fixed constant value like 0 or something like that? Yeah? It's very specific to the connection, so it's going to be harder for an attacker to guess what the MAC would be. There's some missing piece that's not quite there yet, though, because a MAC is like a long value that's hard to predict if you don't know the key. Yeah? Oh, it'd be the same for everyone because it would depend only on the password. It'd be the same for everyone. So an attacker who observed you connecting to the network could copy that same MAC for their, and then the access point would think they know the password too, even though they don't. So by making this depend on the nonces, well, by making it depend on the MAC addresses is different for every computer that's connecting. So if I observe some other computer connecting, it doesn't help me like claim to know the password. And because of the nonces, it'll be different every time someone connects. So it can't be reused from like yesterday again today. Okay, so that's why they use a MAC on all of the data sent so far. And then at the end of that, hopefully both sides should be confident that the other side knows the password. And so they're authorized to be part of this network. And then basically packets are encrypted. Any packets now after this are encrypted and MAC'd using the PK. But there's one more detail, which is we need the way to send broadcast packets, like for ARP or DHCP. So to enable the client to send broadcast packets, there's actually a separate key. Broadcast packets are encrypted under this GTK. So if the client wants to send data to the access point, it can encrypt it with the PTK. And if it wants to send data to other devices, a broadcast message to all the other devices, it encrypts it with the GTK. What would be wrong with encrypting a broadcast message with the PTK? Yeah? Only you and the router know it, the other devices don't know it, so they won't be able to decrypt it. What if I connect to a WPA2 network and I want to send a Wi-Fi frame to another device on the network, not the access point, but another device on the network? What key should I use? The PTK? The GTK? That would work. The other device would be able to decrypt because all of them on all devices on the same network receive the same GTK. But it would mean that other devices on the network could eavesdrop. The other alternative is that I encrypt it with the PTK and send it to the access point and have the access point send it to the other device. Okay, so this is the handshake. That's what's done when connecting to a network. It's maybe a little bit overcomplicated, but maybe you get some feeling for why the pieces are there. All right, so what this means is that if you know the password, you can join the network. If you know the password, if you know the password to the network, can you decrypt traffic that other devices on the same Wi-Fi network are sending to the access point? You're malicious. You're a malicious attacker and you do know the password. If you're a malicious attacker and you don't know the password, you're not going to be able to decrypt. If you're a malicious attacker and you do know the password, can you decrypt messages sent by other devices on the network? Only the ones that were broadcast for sure. If they're broadcast, then they're encrypted with the GTK, which is known to all the devices. So then for sure, the attacker can decrypt the things were broadcast. What about non-broadcast? Yeah? Because of the nonces. Do you want to say more? So no, the attacker can't. Because the attacker can't know what the nonces were? Something wrong with that argument because the nonces are sent over the radio waves. So the attacker can know what the nonces are. An attacker on the network can listen to all messages and the nonces are not encrypted. It's like the PTK the other device is using is hash, so you can't recover it. Can an attacker recompute that hash? What does it depend on? Can an attacker learn what the PSK is if the attacker knows the Wi-Fi password? Yeah, because the PSK depends only on the Wi-Fi password. So can an attacker learn some other device's PTK? Depends on the PSK, which you said the attacker knows. Depends on the nonces. Can the attacker know those? Yeah, because they're broadcast. Depends on the MAC addresses. Can the attacker know those? Yeah, they're in the MAC frames that are sent where these messages are sent. So all the inputs to this hash function, the attacker knows, so the attacker can apply the hash function themselves and recompute the TK for some other device. So if an attacker knows the password and is eavesdropping on this handshake, can infer what PTK other devices are getting, and then use that PTK to decrypt the data those other devices are sending. So this WPA2 still allows an attacker who does know the password to eavesdrop on all the data. Does that make sense? But what it protects against is an attacker who doesn't know the password. Yeah.
I was gonna ask why we this at all, but
Yeah, in some sense, it's not clear that we really, really need it. I can't really give you a good argument for why. Do you have a good argument for why we need it?
harder. Like, I know the password is not one. Or anything, but
Yeah, I'm not sure. I'm not sure if there's a value. You could imagine just using the PSK and being done with it. And I'm not sure if this is that much better than that. Not sure. Anyway, this is the design. Yeah. It does make it so that the attacker who's not there for the handshake won't be able to decrypt even if they know the password. That's true. Yep. That could be a benefit. Good point. Okay. Now that's the conceptual handshake, but this you'll notice involves 1, 2, 3, 4, 5, 6, 7. It turns out that can be optimized. The number of messages back and forth can be optimized, which enables you to connect quicker to the network. For instance, the S nonce does not depend on the A nonce, right? So the client doesn't need to wait until the A nonce is received. The client could just send the S nonce right away. Just as good. So the client could send the authentication request, and then immediately I know what you're going to need from me next. Send the S nonce next without waiting. And if you're going to do that, they could just be combined into one message. Single message has both the authentication request and the S nonce. So you can combine some of these messages together. Conceptually, it's easier to think about it this way, but then when you bundle them together, you end up with something that's a little bit simpler. You like bundle together multiple messages. And then you end up with something instead of 7 has only 5, I guess. So this is the actual protocol. Okay, so what are the vulnerabilities? One vulnerability is if you know the password, if Mallory knows the password, Mallory can pretend to be an access point and then become a man in the middle. Everybody's traffic gets routed through Mallory. Actually, you could have already known that. If Mallory knows the password, Mallory can mount these ARP and DHCP attacks by like recovering the PTK that someone else is using and then doing ARP or DHCP attacks. Just another way to achieve the same end. Another vulnerability of WPA2, and this is a bad one. This is a serious vulnerability, is that most people choose passwords that are semi-guessable. Because we like try to make them memorable or whatever, it's just easier to write them down. And you end up with passwords like let me in or a guest or I'm here or whatever. Okay, so the vulnerability that enables, it enables offline brute force attack. Of course, one way to try to get into a Wi-Fi network is to try connecting many times, trying a different password each time with a guess at what the password might be. That's kind of obvious, but that's kind of slow. If I can if I think I've got a billion ideas for what the password might be, and I got to try them one by one by doing this like a network connection, it's going to take me a long time to repeat this 5-message interaction once for each of the billion possibilities. But a smarter thing the attacker can do is the attacker can eavesdrop, capture all of this data, and then when they have a guess at the password, they compute like the implied PSK based on their guess, and then the implied PTK based on their guess, and then the implied MAC, and check if the implied MAC matches the actual MAC that was sent. And if they got their guess right, then they should be like computing the MAC correctly. And if their guess was wrong, the MAC will be wrong. And so they can very quickly confirm whether their guess is right or wrong by doing a few, like hash or slow hash computations. Now, ideally, the PSK would be derived from the password by a slow hash, except I'm not sure they actually use a slow hash. I think maybe they use a fast hash. I'd have to look it up, which makes these attacks even more feasible. So an attacker eavesdrops and captures one connection request from one legitimate device, and then can try lots of possibilities for what the password is and reconstruct what the password is, if the password is guessable. So that's a serious problem, and there were attackers who would go around. It's called war driving. You would drive around in your car with a laptop that was recording traffic from all the Wi-Fi networks, and as you drive around, you encounter a whole bunch of Wi-Fi networks, and you use your GPS and you map out where they are, and you start trying to use this attack to offline try to find Wi-Fi passwords for the networks that you saw. Sometimes you're successful. Another weakness in WPA2 is that there's no forward secrecy. An eavesdropper who records this initial handshake and then later learns the password can decrypt old traffic. Maybe not a big deal. I mean, this is not the highest security mechanism in the world, but just pointing it out. Okay, so WPA2, probably good enough for home networks, but it has these weaknesses, these weak points that come from the fact that there's a single shared password, which might be guessable, and everything derived from that password, which then enables offline attack. So recognizing there's a problem, the Wi-Fi standards folks designed an alternate protocol called WPA Enterprise. This is an alternative cryptographic mechanism. Same deal. You want to authenticate who can access the network. Everybody ends up with a PTK that they can use for encrypting and macking packets, but they use a different process to end up with the PTK. And so companies, including Berkeley's Care Bears, Eduroam, whatever, are typically using this WPA Enterprise. And the approach there is, instead of a password, but if you know the password, you defeat it, that's it, you're in. They rely on some existing authentication mechanism. So here we rely on CalNet. So when your laptop first time wants to connect to any Berkeley Wi-Fi network, first you have to log into CalNet. Then CalNet verifies that, authenticates you. And that's done with some cryptography, probably some public key cryptography. Or, well, I guess maybe your username and password and your two-factor authentication, I guess, from your Berkeley CalNet account. And then once the authentication server has verified it's you, it can then generate a temporary key and send that to you and send that to the access point. Encrypted appropriately, encrypted under your public key and encrypted under the access points and public key, or encrypted under a symmetric key that the authentication server shares with your device. So now, once you authenticate the CalNet server, you and the access point end up with the PTK, which you can then use for communicating on this Wi-Fi network. Okay, so now this solves the problem of offline password guessing. And yeah, we don't. You authenticating and gaining a PTK for your machine does not let you derive the PTK that other machines are using, and so you can't easily decrypt the traffic that other machines are sending. Okay, so this is a better, higher level of security. If your company already has some existing way of authenticating users, some authentications. So this then defends against the weaknesses that I was mentioning of WPA2. Well, the first thing that I showed you was called WPA2 PSK, pre-shared key. Anyway, defends against the weaknesses of those. It can't, attacker who, there's no way to do the rogue access point. Because just because you can log into CalNet doesn't give you a way to learn a PSK that everyone uses. There is no PSK that everyone uses. Every person has their own individualized PTK. And there's no brute force attack because, yeah, it's just a random cryptographic key that's generated for you. And, well, okay, it still doesn't provide forward secrecy. So that's one of the goals there. Okay, so higher security, but still vulnerable to ARP and DHCP spoofing, so it's not perfect. So the summary here is we looked at some of the lower level network layers. And when you look at them in detail, what you discover is that an attacker who's on the network can elevate themselves to man-in-the-middle attacker. And basically, there's no security. There's no security against someone with physical access to the network or in radio range for wireless networks. And so basically, yeah, we got no answers for these security problems. And the resulting security problems at the low levels are going to have to be solved when we start to look at the higher level protocols. So that's what I'm going to do next lecture, as I'm going to start to look at security vulnerabilities and solutions at higher levels, the IP and the TCP and the application layer. Okay. So we'll stop here. Thanks very much.